Yeah, I think it is recorded. So
Yes,
it will be available on YouTube. Yes. Yes.
Okay.
You are not recording. Okay,
Yeah.
you are now.
All right. Well, it is a very narrow audience this time, so there isn't really a great need to explain who I am. My name is Boris Shingarov. I work at Labware. I've spent forever building VMs. Specifically interested in formal verification of VMs and certified correct VMs, and have been talking about how just testing is absolutely not enough for constructing of a reasonable Smalltalk VM. And how TDD is generally considered harmful, and all of these companies that are doing tools about code coverage and all of that is, you know, I'll give you somewhat somewhat of an example that maybe you will think it's contrived, but something really very close to this actually did happen in reality with a major Java VM vendor and with a contractor that they were trying to implement some VM primitive. So they would do implementation and they would do tests. And with the Java VM, it's this, it's a bit specific because of the process, how Sun has this very detailed, spelled out, this lawyerish process of how you have a reference implementation, and you have this very spelled out technology compatibility test suite, and what they think is very scientific measuring of test coverage. And it does spill into actual legal contract language. And so it went something like this, and I'm specifying for simplifying for exposition, but this is really only slight oversimplification, and it's not very far from it. So let's say something really simple. And as small talkers, we're not gonna now concentrate on things that we're in a live environment, and if primitive plus does not work at all, then the whole Smalltalk doesn't work at all, and then we cannot even run that. No, let's not talk about that. Let's say we're in ULD, and if the VM is completely screwed, we still can debug, and that's another thing, right? So let's say we want to implement plus in integer, right? So we're good TDD guys, and here on the left we start with a test, right? So we go test. Oh, okay, let me bring this down a little bit. So test 3 plus 4. And we self assert 3 plus 4 equals 7, right? So that was the first piece of Smalltalk code that ever ran. So we're gonna pretend we're there. And we try to implement it. So we implement it, well, let's say in integer plus, and we just want to satisfy the test, right? So we just return 7, right? So does this succeed? Well, it does, right? So we ship to the customer, and let me remind you, this actually happened 15 or 20 years ago with an actual major Java VM vendor contracting to write a slightly more complex primitive than this, but it's I mean, I'm only slightly exaggerating here, right? So the contractor turns in the test, the code, and demands the money. And the vendor says, wait, you must be kidding, right? What the hell is this? And I say, well, look, we said that we write exhaustive tests, which this tool that not we, you told us to use this tool as the measure for code coverage. And the code coverage is 100%, right? We do cover 100%. And all of this is passing. So you either pay us, or here is the phone for our lawyer on whom you can serve the documents. And the vendor's lawyers reviewed the contract and said, well, yes, they are right. We have to pay them. So I said, okay, here's the money, but we will pay you extra to fix this bug because our customer now complains about 2 plus 2 evaluating to 7. Okay. How about a new test? Test 2 plus 2. Self-assert 2 plus 2 equals 4. Okay. Let's fix the code. Self equals 2 if true, return 4. Did we fix your bug? Yes. Wait a sec. You must be joking. This is not what we meant. This code is bogus. It doesn't do plus at all. Yes, it does. This is what the contract says. Okay, I guess we must pay you money. But now the customer is complaining about 42 plus 1 being 7 again. Oh, yeah, okay. Oh, we did this before. This is a very, very traditional and very well working process now. Test 42 plus 1, self-assert 42 plus 1 equals 43, and self equals 42 if true. Answer 43. Now, so I spent decades trying to argue that this TDD process is fundamentally flawed. You cannot do anything with this. You cannot construct correct software through just testing, and you need formal verifications, and there are mathematical reasons why this code is wrong. And I spent 3 decades trying to understand and spent with the optimizing compiler community, with you know, what is the research and why fundamentally this code is not is fundamentally wrong as opposed to just doing a plus, and you know, there's reasons which have to do with the intuitionistic types and how this expression that we wrote, that this if then else expression which we wrote, is not functorial in its arguments, and all that nice stuff that everyone working on compilers have been making progress in the last 40 years. And today we'll look at this from a different angle, which is Kolmogorov-Chaitin complexity. So the length of the shortest program that will compute this, or the length of the shortest program that will pass these three tests. You see, we'll worry about tomorrow's talk about what exactly shortest means and how to measure complexity of this, and why and what are the elementary blocks that what they must look like for the measure to make sense, and what difference does it make if a formula is convex versus when the formula is non-convex. But today we'll just notice simply that this program is actually longer than just saying, you know, using the available processor instruction to implement the plus. So we will concentrate on the fact that the actual reason why this is wrong is simply because it is longer than the correct program, and in particular, it is even longer than the shortest program that will pass these particular tests. So you see that this VM primitive that we wrote here is this is a combination of some building blocks, such as some processor instructions. So the question I will be asking myself today is, can I algorithmically compute the shortest program that will satisfy what I wrote on the left? And what I'm looking for is automate all of this multi-step bargaining between the VM vendor and his lawyers, and the contractor and his lawyers. And these algorithms are actually well known. They have been well known for the very long time, actually. So obviously, I don't pretend that I invented any of this. All I am aiming at is how we can do this with a very tiny amount of Smalltalk code, and I will show you the code, and you can download it from GitHub, and it's all open source, and everything is open source here. And then I will explain why this is central to solving our problem of creating Smalltalk for the future. So what do we need to start? So we assume that we have some kind of blocks out of which we construct our program. So let's say processor instructions. And let's assume that we have some way of specifying the correctness of the program. That is, we have some kind of verification oracle, something that will say, oh, you missed a case, right? So if I only have only this here, then I will synthesize this return 7, and then this verification oracle is gonna tell me, no, you missed that there is a corner case. 2 + 2 does not compute to 4, and then what we're gonna do is we're gonna add this counter example and say, no, your program that you synthesize must also compute this correctly, and then we repeat this process until verification passes, and then at that point we have enough examples, and these examples, they are they have enough of a test suite, and we know that it is enough of a test suite because the test oracle cannot find any more counterexamples. So this is the cycle how we do this. So you give it the example of 3 plus 4 equals 7. It says, nope, you missed the case. 2 plus 2 does not equal 7, it equals 4. You give it this, and you do this. You do this until you're done. Actually, I'm gonna switch to a little bit different example, because with this plus thing, it kind of misses the point, because the interesting stuff is hidden inside the plus operation, right? So if we are given some kind of algebra, right, there are operations, and these operations are opaque symbols. And what we're interested in is how these symbols, how these operations compose. And we actually want to ignore what's inside. So let's use this example. I'm gonna get rid of this page and get a new one. So let's say I want to do something that will compute this, right? So for all x, it will just take x, add 2 to it, and put it back into x. I will demonstrate with 2 elementary blocks, out of which I will be synthesizing this. Let's say my elementary blocks are add 1. It's one block, and the other block is load 2. So add 1 takes x, adds 1 to it, and puts it into x. Load 2 discards whatever was in the x and says, well, x from now on is 2. So what's gonna happen is, so we give it some kind of x, and we ask the verification oracle to, well, give me some x and some example. So we will start with the first iteration of the cycle, where x equals 0. And we want, at the end, we want it to compute that x equals 2. So the shortest way is 1 instruction. So the algorithm is gonna make a constraint, which I will show you how I make these constraints in Smalltalk. And we'll say, okay, well, how about add 1? Nah, that doesn't work, because x equals 1. And we want x to be 2. So the oracle says, no, this is no good. We don't even have to ask the oracle. No, we just straight compare on the test. The test fails. Now load 2 is our shortest program now, because x equals 2 at the end. Now I do verification. I ask the oracle, did I miss anything? And he says, oh, but it doesn't work when x equals 1. So in that case, x needs to be 3. Now I am searching for a program that is 1 instruction long, and I come to the conclusion that there is no such program, because in this case, this gives me 1, and that's wrong, and this gives me 2, and that's wrong. So that's bad. Load 2, this test passes, but this one fails. So n equals 1 I cannot do. Now, how about n equals 2? I can have several different programs now. I can have 4 different variants, right? Add one, add one, load two, add one, and load two. And the nice thing is that I can use a constraint satisfaction algorithm that doesn't lead to this combinatorial blow up, that the constraints immediately tell me that, okay, well, already on this first one, you have only 3 possibilities, because if you load 2 and then add 1, that's no good. So the first test gives us either add 1, or it gives us add 1, load 2, or it gives us add 1, add 1. So we now look at these guys and right, yeah, load two here is the third one. That satisfies the first one, but only this one satisfies both tests, and this is no longer working. And now I take this program to the verification oracle again, and it executes this program symbolically and comes up with x plus 2, and this is symbolically or algebraically always equal to what we want. And he said, yep, there is no counterexample. The SAT solver comes with unsat, and we are happy. And this is my program of the shortest length. So now, what Smalltalk objects do we need for this synthesis most generally? So I need program, I need program text, I need states, I need available blocks, I need some kind of description what each block does. I need obviously the verification oracle that will tell me whether my program is doing what it's supposed to do or not. And I have to have a model of program execution. So let me go to another page. So I have a number of states. So this is state 1, state 2, state 3, and in the program text, I have instruction 1 here, instruction 2, and I have some time here, and you know, at time equals 1, the instruction at this is I1, and at time equals 2, I have instruction equals I2, and instruction I2 transforms S1 into S2, and instruction 2 transforms S2 into S3. And what I want to do is I want to decouple a completely abstract notion of how a program relates program text to execution. So this concept that at each step, right, at each t of this time t, I have instructions, and instructions, they relate properties of state, not just the states themselves. And this is what I need to do program analysis, as in this classical book. I think it was like in 1980 or 81 by Muchnik and this Cousseau, you know, that they do program analysis by transitioning from the concept of what's inside the states to invariance over the states. And you do that by looking at the behavior of the program as this is a Poincaré dynamical system. right? So it's a rewriting, process, and it induces like basically the semantics of each of these instructions. These are your Newton laws, and at each step your physical system evolves. And in order to decouple this from how I express what blocks I have available to me and what each block does and what the program should do, for this decoupling, I use constraint logic programming. With logic programming, you see, I'll talk momentarily about the SAT revolution and then in general the computing revolution that has been happening in the last like 15 years in a moment. But what I want to say now is your logic programming in the 21st century is there's a world of difference with your logic programming now versus your logic programming of the Robinson era of the 1960s. We've got it's quite a different world of what is possible now with that. So how do what do we express this? Well, this is well, first of all, we have to express some of the blocks, right? So that instruction, my add one is an instruction, and load two is an instruction. So this is going to be some sort of problem instance, and I will specify a constraint that if the state at ti is si, state at ti plus 1 is state I plus 1, then I have a constraint that I push out into some formula that is computed from a Smalltalk block that I will show you just in a couple of moments. That this is that si by the instruction I goes into state I plus 1. Well, in general, these are like Floyd-Hoare verification conditions. We don't want to do them. We just want to do the constraints that the semantic of the instructions are imposing of the relationship between this and this. But for now, for simplicity, we're just gonna write it like this. And then there are instruction semantics, right? So if we have at moment I the program text at moment t is I, then there is, and we express it as a Smalltalk block that evaluates to some logical condition, is that what the semantics of which instruction, right? So that si of this, this I is going to this I plus 1, and this is inside these quotes, in the sense that we cannot really, this is outside of the logical scope. This is in the, oops, sorry, maybe you cannot see this. This is outside of the logic. This is inside the theory which we express in Smalltalk, and I will show you right now. So let me fire up. This was in this is Bootstrap and Fero UI Bootstrap image. So we have that. Oh, I need to share my screen. So how did I do that? Share screen. Host disabled participant screen sharing. Leandro, can you enable me to share my screen?
Oh, try again.
Let me try. What? Oh, okay. This should. Can you see my screen?
Yes.
Perfect. Let me get rid of this window and right. Okay. So this is this counterexample synthesis. This is all available on GitHub, as everything that we do in our project is not only this, but absolutely every. This is jumping. Wow, this is jumping really badly. I don't understand why there is now suddenly a lag. Okay, well, whatever. So, and in the hackathon, we will show how to download all this and exactly which repositories you have to take. But Jan has a shell script that just gives you an image like this. So I'll just walk through this. So we're gonna look at this this example of this. So add to, and here we just use Floyd Hoare pre and post conditions and nothing really nothing really more advanced. We will see how this is not enough, and tomorrow we will talk about how we have much better ways of doing this. But this is just we can write them like this, or we can write yeah, it's the same. Yeah, that we just say that the new state must be this old guy plus 2. And then we have in the test, we say that it's just a dictionary, and this add 1 and this load 2. They are some objects that know how to transform state into state. This work in add 1, it takes the old state and returns old state plus 1, and load 2, that's just to, actually this is not needed, to int, it can be just return 2, but doesn't matter. And let me show you the actual cycle, what happens here. I will debug the test. And so I'll obtain a so now this Segis guy knows that I have 2 commands at my disposal, and these are these commands names. And inside there, the only thing that it knows is that it's basically a Smalltalk block that goes from an old state to a new state. And let's see what we do with this, how this synthesize actually works. Let me make this a bit bigger. Okay, I think you can see here, right? So we synthesize the spec class is this what I just showed you, right? This program spec IS, and the anyone is just this initial seed of the synthesis. So I step in. So synthesize him, right? This spec, given exactly the example inputs. The example inputs is this one item that it has to work with x equals 0. That's what I showed you, right? Now, how do we synthesize this? Well, we first go like this. For all of the example inputs, we do these closest chains, right? So basically that S1 has to go to S2 correctly for each of these example inputs, of which now we only have one. So we have one chain now, right? That, so that true that this state that has 0 will go to 2. Actually, it's the other way around, right? That 0 will go to 2 plus 0, and we have not simplified this, so this is just whatever the SMT solver gave us back. So now this is the specification formula, which is what needs to be satisfied. That basically tells us where is this? This is tiny, and people have asked me to make the fonts really big. So yeah, there it is, right? So it's just add of all of them together. And the chains, they are just what's on the left. And then I go to an external solver for ASP, which is this EasySMT. It's an interesting resolution engine that does constraint ASP on top of whatever SMT engine you might have. And the SMT engine we call back into the machine arithmetic, which is a wrapper. There is Z3 on the bottom. On top of Z3, we have a set of FFIs that allows us to call that from Smalltalk. On top of that FFI, we have some objectification layer that allows us to do interesting Smalltalk things. So a expression that evaluates to some kind of Boolean, and then you send it if true, if false, and that transforms it into an if then else. And you know, if you have a something like a list, which is either nil or a cons, it becomes an actual data type in Z3 and that kind of stuff. So you can express constraints as this specification formula, right? So that the specification formula needs to be satisfied with these things, and you pass that to there, and the program is what we just wrote on paper, right? That the program text This means that there is exactly one rule like this, and each instruction mutates these chains at the moment into this state at the next time. And we'll go back, and right, so that, and we solve that. The solver comes back with the answers, and let me show you the answers. And this is one answer set, and here is the synthesized program, which is load 2, right? For the one thing, this is the shortest thing we can do, and then we just answer a program with this. And if the candidate is nil, then we don't do anything. And then we verify. So we verify. Let me go through this to show you what's happening here. And if the verify, it can either succeed, right? So we just ask for the instance of another Z3 solver, and we prove valid that the precondition always leads to the post condition. And if we can prove that, then we're fine. If we cannot, then that throws an exception, and right? So that is now, it throws not valid. And here is a counterexample. And the counterexample is that, well, what about x is 1, which is what I just showed you. And then we, right, what was, I go through, right? And now right, so this is the result is, oh, I did, right, I am still at this one thing, right? So now I synthesized, why is my, no, I skipped, that's not of one item. Why is this? Yeah, this is, did I? Okay, let's see. This is actually, yeah, that's, let me show you this again.
Boris, a question.
Yes, of course.
So can the solver return with more than one, say 2 answers, or is nothing or one? Because there might be 2 answers.
Oh, it can. Oh, absolutely. It can return with more programs than one. Yes. Yes.
Okay. And in that case, what do you do?
I just ask for any one, right?
Okay.
I'll show you in the code right here, because I want you to understand how it works.
Okay.
And I just either clicked on over rather than through or something like this, because the first time, right, this is the synthesized given any one. So this is the first time, right? So this is only with, and this is given exactly those inputs, right? And if we are given exactly, right, my candidate here is this thing which is still too short, right? And then when I verify, the verification fails, and I want to show you how it synthesizes in the next iteration, because that's the interesting case, right? So on not valid, do the synthesize of example inputs, comma, and this other counter example, right? The one that the verifier gave me, that, oh, you were missing an edge case. Right, so I want to go through this actually. If I go through, and I want to yes, okay, yes. So now I have a candidate, right? Now I have the counter example, and I go again into this synthesize. I recursively go into it with this, but now my example inputs are now 2, right? I have to work with x equals 0 and with x equals 1, right? And now I will show you exactly what right? So if these are my answers, and I just go from these answers, I select only one. Right, so if it's empty, then I return nil, and then I retry with bigger ones, which is what's happening here, right? Because this is still n equals 1, right? It's too short. And then, right, it's, right, I go fuel +1, and if I am bigger than my maximum length of the problem, then of the program, then I am search depth exceeded, and then I recursively try to resynthesize again, but now my fuel is 2 instead of 1, right? And in this case, let me show you the synthesize. The candidate program is, here's the answers. Now the answers, all of this. Is not empty, but I just go answers anyone, right? That's the answer to your question, Leandro, right? So I just.
Yes, but my next question is, could it happen that the one you select from this collection of answers is invalid, but another one from the same collection?
Oh, no. We already verified.
Okay.
We'll at this point we verified, right? And this is our, yeah. Right. And then this is our result, and this is the program text. Add one. So that's how we how we do this, and yeah.
Sorry, can I make a comment?
Yes, sure.
So I think what Leandro was asking, but I don't know, Leandro can say it, but I think what he was asking is that maybe you had a better answer in your set and you are just picking one and you are not picking the correct one. But I think what is going to happen is that then the set solver will give you a counter example, and you feed the counter example, and the next time you get the answer that was already in your set, but you did not pick. Is that correct?
Oh, it is correct. Yes, yes, yes. You have no way with counterexample guided synthesis. Even in principle, you cannot have if you have just a set of tests, right? If you have a set of examples, and you're trying to synthesize a program from a set of these tests, there is no way to know that your program, like which program is better than another program, right? Because at that point, you're not verifying. You're just looking at a particular set of tests. And the reason why you cannot simply ask the synthesizer, oh, give me a program which satisfies that verification condition has to do with divergence, right? With halting and with decidability. Because in those inside those verification conditions, you are going to have a bunch of quantifiers, right? Like for all blah 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 exists blah blah blah, and inside those for all, there are going to be a bunch of terms, and outside of this, you're going to have again a bunch of logical formulas. And once you go from these decidable theories that Z3 can for sure satisfy or prove unsatisfiability, as soon as you go into this quantified first order logic, then it stops being decidable. So now you are at the mercy of luck. That is what really what really happened in terms of progress in the last 20 years, that now we have well-established algorithms that guarantee that the algorithm will actually converge, and it will never go into an infinite cycle of trying to prove, well, basically a Gödel point, right? That's the reason why we are stuck with gradually adding these tests until we've reached this fixed point of no matter how many other counterexamples we are gonna add, well, we already satisfy the spec, so it's gonna, you know, it's gonna give you always the same program. Any other questions before I quickly go into giving you a context why we're doing this, and also then there is this other half, what do we do with this in practice? Like I just wanna kind of give sort of a closure to the question of how we do synthesis.
I have a simple question about this maximum sequence length.
Yes.
So how do you come up with a value for that? Is something you somehow calculate?
At this point, it's just empirical.
Okay.
It's empirical, and it's simply to avoid divergence to maximum, and I will show you, especially tomorrow, we will talk about converging and diverging cases, and how to guarantee that we don't go into any kind of infinite loops. But in this case, we just have to artificially bind this to some kind of maximum length that we don't just search for things infinitely until we, I don't know, run out of RAM or something.
Okay.
Okay, let me step back a little bit. We're not doing on time really well, but we can use a little bit more time. So, and tell you what it is we're doing in general in terms of context. We are inventing the small talk of the future. And this whole effort started from a conversation we were having with Dan Ingalls a number of years ago about Smalltalk 80 versus Smalltalk. That the problem is that Smalltalk 80 is not small talk, and when I heard that, when I heard Dan Ingalls say that, the first thought that was a recollection in my mind, how at the turn of the century we were at OTI then. We were starting the Eclipse project, and we were given this mandate from the higher ups at IBM, saying that, well, look, guys, we were very successful with COBOL. That for 30 or 40 years, this was the golden standard for what programming is and how people program computers. So your mandate is to build something like that for the next 30 years. And there we were with this, you know, everyone with massive Smalltalk background, trying to invent this COBOL for the new century. And that's what, you know, Eclipse based on Java, that's what it is. And I'm not saying, you know, obviously it was not meant, you know, to invent something as horrible as COBOL, but it was, I mean, it was in terms of how successful it should be. But I never thought about this, you know, other than this framework of you know, just it being successful. And then when Dan Ingalls said, well, look, because this is not small talk, right? Then I understood that this is not just about success. It's about fundamentally different motivations of small talk and of COBOL. Right. So in what is the fundamental motivation in the COBOL process is there is this conveyor belt, and on this belt there are they travel bugs, right, left to right, and your job is you pick a bug from the conveyor belt and you do something to it, and it's a reactive process, as Alan Kay would say, right? There are these mental processes that are reactive, and then there are mental processes that are cognitive, right? So when you're fixing bug number 1 and then bug number 2 and so on, and bug number n+1, this is a reactive process, which you just, there is an existing process, some SOPs, and you do something to the bug and it gets fixed. And when you're done the nth bug, you pick the n+1st bug from the conveyor and you repeat in this reactive way. Now, the Smalltalk process is something else altogether, right? Your job is to invent the future, and how do you do that? Right, like you don't have an SOP. What you do is you go to this land where the sea makes an arch, and there's an oak, and on that oak is a golden chain, and on that chain there is a cat. So this magical cat, when he goes right, he sings songs, and when he goes left, he tells stories. And your job is to not forget your pen, because your job is to write down one of those stories and you bring it back with you. That's how invent your future. Now, you don't do this alone. There's a number of things that changed since the 90s. My favorite stories with this Scamp article in Smalltalk Report 94 by Alan Knight about this Smalltalk KeyCast mega processor that you do this silicon completely dedicated to Smalltalk execution, and it still has no chance because of economy of scale to compete with I don't know, Intel or whatever general purpose chip, simply because of economy of scale. And this is no longer the case. There is now this global team who is working on the computational platform of the future. And this is very different because dynamic languages are now where the economy of scale actually is. So there is there is teams like Open Power and RISC-V, and RISC-V is the continuation of the Smalltalk on a RISC SOAR project, and we have this J extension group, for example, where Giselle and myself and Martin Maas and a whole bunch of brilliant VM guys, much smarter than me, inventing this Smalltalk processor of the future, essentially. And the approach that is being used by this global team is very different than what you would think about in the classical thing, because a number of things have changed in the last 15 or maybe 20 years, arguably as important as the invention of computer by Turing itself. It's, you know, when with the invention of the computer, you now see that certain things that were thought completely impossible at all before, now they are seen as being possible. Well, we have things now, for example, with the new algorithms for SAT solving. We have algorithms that make solving of problems possible that 15 years ago was completely like, yeah, well, this is exponential and we know it's exponential, and unless p equals np, this is completely computationally intractable, and just forget about it. And yes, these algorithms, they're very, very theoretically interesting, but they have absolutely no bearing in general, in general practice, right? Like in practical terms. This has changed because all of this, we now have algorithms for SAT resolution that we can recognize that this is a special case of the decision problem, and we can actually use that for actual practical synthesis of actual practical compilers. We have specifications of real processors from which it is easier and more practical to derive an optimizing compiler than it is to write it by hand, because we have ISAs where you cannot reason about the behavior of the processor because they are not ISAs, strictly speaking, because the classical definition of ISA is that you have coherence, right? They are strictly they're strictly coherent specification that say, well, you know, if the processor executes this instruction in this state, you are guaranteed to have this state at the next step. And this is true of IBM 360, and this is true of Intel, but this is not true of today's modern processors that are designed to perform massively parallel computation. And the reason why this is so is because you have memory coherence, and even if we are not talking about caches, even when you have just a superscalar processor, you still have reorder buffers at as the last stage in the pipeline, and the optimizations that the reordering does, they leak. Well, you can do something like IBM 360 or Intel, where you say, no, you are not allowed to leak these microarchitectural optimizations into the programmer visible effects. But then as you scale your number of like the amount of parallelism, you are basically grinding your performance to a halt. Or you say, no. The compiler writer cannot rely on full determinism, right? So you're not given exactly what your next state is. There is only these constraints on the envelope of all possible behaviors that the different implementation of the processor might have. And then it simply becomes intractable to reason about this manually. And now you are really limited to what kind of optimizations you can do. So what we're doing is we take, like, we're way out of time. So Jan is gonna show on the other side of the of the world how we take specifications of new ISAs like RISC-V, OpenPower. ARM are doing the same thing, although we are not really experimenting with ARM a lot. How you take a specification of that processor, and this becomes our available blocks, right, in this case. And the idea is that we take these two halves, and at the hackathon, we will connect them together, and we'll see how you come up with a synthesizer that is derived from the spec. Well, what is left, I'm just giving an overview of the rest of the schedule, is the best way of how to specify the behavior, because what I showed you now is deficient in the way that, well, this spec, right? Well, generally speaking, this does not scale. This only works for this is classical Floyd-Hoare preconditions and postconditions, and this does not scale beyond toy example. And I will talk about why. But we'll see, depending on, we still have 45 minutes of like break and free form discussion and Q&A for it depends on what you guys are most interested in. This is not a, I don't know, 200 people audience that I was afraid it might be. This is a much more friendly, and you know, I hope this is going to be much more interactive. This is
so Boris, would this be a good time for a short break?
For sure, yeah.
So if we break for, say, 5 minutes, then when we come back, we can spend the rest of the hour with some discussion or whatever you have in mind, and questions, etc.
Yeah, I mean, I would like this to be more of a question driven then, and I remember Javier was telling me, well, I want more details, right? So, I mean, I can talk about this for days and weeks, and it depends really what you are most like, which details you are most interested in.
Okay, let's break for 5
let's
minutes.
do a break and then come back at 21
Yes.
minutes.
Okay, 5 minutes.
All right.
Bye.